Well, this is our lecture on chemical reactions, our first lecture. We're like 40% of the way through the class in chemistry, and this is the first time we're doing chemical reactions, which kind of feels a little embarrassing. But I do like this class format because it helps really establish what atoms and molecules are before we start manipulating them. But that's what we get to do today, and it's really exciting because it's going to feel like we're doing chemistry now, right? So let's start by looking at this sample chemical reaction right here. In the chemical reaction, we have reactants on the left-hand side of this equation and a little arrow to show this is where they are going to, where they're forming. And then we have products on the right-hand side of the equation. So reactants go to form products, and this little arrow is just showing you kind of what direction this reaction is going. And we are changing, you can tell this is a chemical reaction because we're changing the identity of the species here from one thing or two different things to two different things, right? Their identity actually changes. Here I have propane and oxygen, and those go to form carbon dioxide and water. This is actually a combustion reaction. This is what happens with your propane tank if you're out grilling, right? You release the propane into the grill. There's oxygen in the air. You give it a spark, it starts to burn, and it's going to produce carbon dioxide and water. Any questions about the format of how we draw chemical equations or chemical reactions like that? Actually, not so much a question, but let me draw your attention to this. We know that propane reacts with oxygen to make carbon dioxide and water, but why did I draw as O2? Why not just say it's reacting with oxygen? I mean, elemental oxygen, it's just the element. And the answer is that there are 7 elements which naturally exist like this. We call them diatoms or diatomic species. And so you need to know them so that if I tell you such and such is reacting with oxygen, that you should know that it comes as O2 and not just O. So diatomic species, things which exist as diatoms in elemental state. I guess I don't need parentheses around that. Meaning O2 instead of just O, right? So there's 7 of them, and there's a couple different ways to remember them. Here's the first way that I learned. I just memorized this funny little word, Oberfinkel, and you can think of that as one of Santa's elves or something. I don't know. It's kind of a silly word, Oberfinkel. But that means if you have hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, or chlorine, then if they're in elemental form, they actually exist as the diatomic species there. There is another way to remember this. If you're looking at your periodic table, I'm going to bring a copy of this in here because it never hurts to have a copy on hand. If you're looking at your periodic table of the elements and you look at all of these elements that like to be a diatomic species, you'll see that fluorine, chlorine, iodine, and bromine, all of these are in this same column. I guess it shouldn't be a surprise that things that are in the same column like to react in similar ways. They each just want one more electron, so it's easy to share with another one. And then we've got nitrogen and oxygen. These just share with the double bond, share with the triple bond. If you outline these elements, which are diatomic species, it makes the number 7. So you count 1, 2, 3, 4, 5, 6. Oh, there's only 6 here, but there should be 7 because it makes the number 7. I kind of point you towards the 7th one here, hydrogen, which of course is often put up here, so that shouldn't be a surprise either. Does that make sense? Do you think you can remember those? That's just an important little thing that you guys need to memorize to know. that those things, they just naturally exist as their dimer forms there. Okay, so we've got these reactants and they go to form products, but there's something terribly wrong with what I've drawn here. Yes, theoretically, propane burns in the presence of oxygen to form carbon dioxide and water. That's, even if you've never seen a combustion reaction before, you know enough about global warming and fuel economy that you might know that that sounds reasonable. But we have a different problem, and that is on the left-hand side of our equation. Yeah, Sarah says it's not balanced. That's our way of saying, look, how many atoms are on each side? Right here, I've got 3 carbons, and here I have 1 carbon. And here I have 8 hydrogens, and here I have 2 hydrogens. So it's like our carbons and hydrogens disappeared. Some of them, maybe they were destroyed in the reaction. But here I have oxygen, 2 of them, and here I have 3 oxygen atoms. So did I make more oxygen atoms? Maybe I converted those carbon atoms and hydrogen atoms to oxygen atoms. Is that what happened? Destroyed carbon atoms and I created new oxygen atoms. No, Sarah's right. No, that's not what happened. That goes against one of the fundamental tenets of atomic theory that you guys memorized back at the beginning of the course. Dalton's postulates of atomic theory, one of them was that atoms cannot be created or destroyed in chemical reactions. So instead of assuming that they were created or destroyed, we have to come up with another answer. And the answer is actually a little bit simpler than that. And it just says, look, if I start with 3 carbon atoms on the left-hand side, I'm going to need 3 carbon atoms on the right-hand side. And so this is telling me if I'm burning propane, which contains 3 carbon atoms, if each carbon dioxide contains 1 carbon atom, then when I burn propane, I'm going to make 3 carbon atoms, or sorry, 3 carbon dioxide molecules for every 1 propane molecule that burns, because that's what I need to do to show that my carbons are balanced on both sides of the chemical equation. They cannot be created or destroyed. Does that make sense? So just to compare carbon atoms, that says, okay, well, I'm just going to need to make 3 carbon dioxide molecules. So I'm going to put, we call that a coefficient right there. And that says that's the number of carbon dioxide molecules that are formed. Now note that it would be wrong to put a 3 down there, right? Ugh, that looks terrible because that changes the identity of the product, and we can't change the identity of the product. But instead, we just say we get 3 of that product. So we're going to put the coefficient right here. Okay, if I play the same game with hydrogen, here I have 8 hydrogen atoms. Here I have 2 hydrogen atoms. So what kind of a number do I have to put here so that my hydrogen atoms will be balanced? Four. That's right. So we have 8 on the left-hand side, 8 in the reactants. I need 4 times 2 is going to give me 8 in the product. And then my hydrogen atoms are balanced against each other, and that's really helpful. Okay. All right, now we need to do oxygen. And I've left oxygen last on purpose. Since we have, and I'm going to put an invisible 1 here. You don't have to put a 1 there, but it tells me that I have balanced all of these against each other. Kind of don't want to change any of those if I can help it. So to balance the oxygen atoms, I just need to determine what to put here, right? So if I have, oh, Sarah's got it, 3 carbon dioxide molecules here, that gives me a total of 6 oxygen atoms represented there, right? 6 O's, because that's 3 CO2s. Each CO2 has 2 oxygen, so 3 times 2 is 6. My water here, each water molecule has 1 oxygen atom, but I have 4 water molecules, so that counts as 4 oxygen atoms, 4 O's. So I have here on the right-hand side now a total of 10 oxygen atoms represented. So I need whatever is here to represent 10 oxygen atoms, and since they come in pairs, I need to put some number here, x, where x times 2 equals 10. And hopefully you guys can look at that and say, okay, I know it's 5. 5 times 2 is equal to 10, and then that should be balanced. Does everybody see that? Does that make sense? Excellent. Okay, so that is our first and one of the biggest aspects to this entire chapter is balancing chemical equations. Okay, and we'll do another one just for practice, and then I'll give you a couple of ideas. There's not this is not like Lewis dot structure where you're going to follow the rules and get the right answer. Instead, it's a little bit more organic. You're going to kind of eyeball it, going to experiment around until you get it right. But this is something you'll all need to be able to do. And sorry, I'm sure that you can do it. So let's try one more here before we talk about some of the rules. I think they'll make a little bit more sense in context. All right, so let's take this one. This is the decomposition of iron 3 chloride into constituent elements, iron and chlorine. And note, I'm making elemental chlorine, but because chlorine is one of these diatomic species, I have to show it as Cl2. All right, and in previous semesters, I've had my students memorize all of the classifications, like this is decomposition and this is combustion, but we're not doing that anymore. So if you see that, don't worry about having to memorize those. But all right, so this one, on first glance, if we move just from left to right, oh, Sarah's got it, that's good. Then it looks like if I have one of these, then I have one of these. I'm just, one iron. That looks great. But then if I move to my chlorine atoms, I have a problem because this FeCl3 molecule represents 3 chlorine atoms and this one represents 2 chlorine atoms. So how could I have the same number of chlorine atoms on each side? Now Sarah's right, she figured it out. This is going to look and feel a little bit like when we were trying to balance a +2 and a -3 on an ionic compound, right? And you had to do the crisscross thing to get the lowest common multiple. We're going to do exactly the same thing. So we're going to say, look, oh, that can't be a 1. If I put the 2 here and the 3 here, then that gives me a common multiple. There's 6 chlorines here now, and there are 6 chlorines here now. Does that make sense? Yes, perfect. Lowest common multiple. And then, as you noted, because I had these two balanced each other, by changing this one, I have to change this one as well. So I'm going to have to go back and make this a 2 as well to make that work. Does that make sense? Okay. Now there's one method that a lot of people use. I don't use it, but it won't hurt me to sit here and teach it to you really quickly, in order that it might help some students, right? So if instead we just kind of eyeballed it, you see that's how I like to do it. But sometimes students are worried that they'll forget that something changed. So instead you'll say on the left-hand side, there'll be a little table and you'll say I've got iron and I've got chlorine, and that on the right-hand side, I have iron and I have chlorine. And you just map it. And so you might start out and say, okay, just to start, I have 1 iron and I have 3 chlorines. Just to start, I have 1 iron and then I have 2 chlorines. And then you'd start balancing it. So this is, I guess, kind of like a table, a little bit like a table, where you're tracking the changes as you go. You're starting with kind of an inventory and then you track the changes as you go. So this is where you'd come along and you'd say, okay, well, I need a 3 here and a 2 there. So would I do that? Now I've got 6 and 6. But I also, now I have 2 here, right? And then you'd come back and say, all right, well, I guess I need a 2 here. So that's going to make this a 2. And then you don't stop until you see visually in your table that everything is the same. Does that make sense? that could be a really helpful tool, especially if the eyeballing it method that I've been doing, you're like, ooh, this is awkward. That could be really helpful too. Okay, I'm gonna copy this. I've got a little set of guidelines. These are not rules. Again, this is not follow the rules like for loose dot structures, but a set of guidelines or tricks that you can use to help balance equations. These are from your lecture notes. I'm just going to copy them in here. So I'm going to move these out of the way. All right. All right. Okay, so rule number 1, any element present in more than 2 locations should be balanced last. All right, so you're always going to expect that the elements are going to be in at least 2 locations, right? Because you're going to have it present in the reactants and the products. But when, for instance, we had oxygen in 3 different places, you're like, well, no, I'm going to wait and do that one last. I'm going to take care of my carbons and take care of my hydrogens first. All right, guideline number 2, any element which exists by itself in an elemental form should be balanced last. So this was another great example to balance this guy last because he's all by himself in an elemental form. If I wait to assign him very last, I can make him anything I want and it's not going to change the balance that I already made with the other carbons and hydrogens. Rule number 3 often throws students off. If you can balance the equation by using fractions, do it. Just put in a half there, put in a 0.5 there, whatever, and take a deep breath and then multiply the entire thing to get a whole number, right? If it's balanced, it's balanced. If you multiply both sides by the same number, it'll still be balanced. But that's much easier than going back and forth to try to balance it using only whole numbers. You probably were taught in a previous chemistry class never to use fractions, and the answer is you can't submit your final answer as a fraction, but you can absolutely use a fraction as a stepping stone to get to the right answer. Rule 4, if a polyatomic ion appears on both sides of the reaction, balance the whole ion instead of doing it piecewise. It won't always appear on both sides, but if it is on both sides, then you can just balance, 3 nitrates here, 3 nitrates there. And you don't have to count individual nitrogen and oxygen atoms because that is a pain. All right, I'm going to add one more guideline to this list of guidelines that I think is important for students. I've observed that it's important. Okay, so number 5, have faith. That might be silly to put that down as a guideline, but when you're doing this for the first time, it's going to feel uncomfortable and you might feel like it's impossible. I can't do it. I can't balance it. But I want you to just, when you hit that wall, take a deep breath and say, it can be done and I could do it. And I just need to keep going. It's just a little puzzle and I can make it work. Okay. So have faith. You can do this. All right. Should we practice a few more? Using our fancy guidelines. All right, let's look at this combustion reaction. We've already done one combustion reaction, but another one will be just fine. And I need to make room for coefficients. It's the number we put in front of the atom, the molecule, so it's the coefficient. Okay, so just eyeballing this as per my guidelines, I know that I'm going to want to balance my oxygen last because it's in 3 locations and because it's all by itself right here. So that will make my life easier. So other than that, I'm just going to move from left to right. Carbons here, carbons here. What do I need in front of the CO2 to balance those carbons? Gonna need a 4. Good. A 4 in front of the CO2 will give me 4 carbons on the right, 4 carbons on the left. All right, if I have 10 hydrogens in the C4H10, then how many waters do I need to give me 10 hydrogens if each water molecule comes in with 2? Good, I'm going to need 5. Excellent. And I've got a little 1 here. All right, so now that I've balanced these, I need to do my oxygen last, have to figure out what goes here. And I have 4 times 2 plus an additional 5. So I have, hopefully you guys can see here, I've got 8 and 5 oxygens in the product side. So I've got 13 oxygens that need to be accounted for. What number can I put here that will make this whole thing worth 13 oxygen atoms? 6.5. Perfect. 6.5. Or I'm going to put 13 halves, right? Because if I multiply that by 2, the 2's will cancel and be left with 13, right? So this is number 3 here. If you could balance an equation by fractions, do it, right? So much easier to say 13 halves. Is this equation balanced? Do I have the same number of carbons, hydrogens, and oxygens on each side? Double check, verify. Yes, I do. There's 4 carbons. There's 10 hydrogens, and yeah, there's 13 oxygens. So now I'm just going to take the whole thing and multiply it by 2. Oops. Oh yeah, and when I do that, then the coefficient in front of the C4H10 becomes what? 2. And then the coefficient in front of the oxygen becomes 13, right? Very easy, 13 divided by 2 times 10. The coefficient in front of the carbon dioxide becomes 8, and the coefficient in front of the water is 10. Easy peasy. We did it. And using this fraction made it so that I didn't have to say, oh, I need 6.5. I can't have 6.5. What if I put in 7? And then I can add an extra water, and then they'll be balanced for oxygens. But then my hydrogens are ruined. So then I have to come back and figure out what to put here to balance the hydrogens. And then my carbons are going to be like, you're going to go around in circles. Trust me, I've done it before. Okay. Just take the fraction and run. All right. Does that make sense to you guys? Okay. Let's do another one. Move this guy out of the way. All right, so we're going to balance this equation. We're taking calcium hydroxide. We're going to react it with sulfuric acid to make calcium sulfate and water. Alexandra, yes. So I multiplied the whole thing by 2. So that's what these, sorry, coming back here. I just put parentheses around the entire thing, reactants and products, and I multiplied the entire thing by 2. And when I did that, I got rid of the fraction. Of course, everything else was doubled, and that's fine. But I did have to get rid of the fraction in order to be completely done and be able to report this to somebody else. Because you can't really have a half of a molecule, right? That doesn't exist. So you can temporarily balance it with a half, but then you have to multiply through to get rid of the fraction for your final answer. Does that make sense? Okay. Excellent. All right, let's look at this guy. This looks terrible. Does this look terrible? Oh my gosh, there's oxygens everywhere. Everywhere, they're everywhere. What do I do? Okay, what do I do is I ignore it, okay, for the moment. It's present in more than 2 locations, so I'm gonna balance it last. That's what I'm gonna do. But not just that, I also have hydrogen in 1, 2, 3 locations. Okay, gross. I'm gonna leave those last. I'm gonna focus on my calcium and my sulfate, and then we'll move forward from there, okay? And I'm gonna have faith, it's gonna work. Okay, so just moving from left to right, but just doing my calcium and my sulfate. Calcium, I see that first. So I've got 1 calcium present here, if I put a 1 there, and again, they could be invisible ones, but I'm going to emphasize it so you can see that I've balanced that one. I've got 1 calcium on each side, so that looks good, right? Now for the SO4, I'm going to use this rule. It says polyatomic ion appears on both sides. I can balance the whole thing. So instead of worrying about every single oxygen, I'm going to balance that as a cluster. Here I've got 1 sulfate in the product because I already balanced it against my 1 calcium. So I want 1 sulfate in this reaction for that, or this reactant, sorry, for that to work. So I've got 1 calcium hydroxide and 1 H2SO4 is going to give me 1 calcium sulfate. My calcium atoms and my sulfate polyatomic ions have been balanced. Is that so far we're looking good? All right, so now we left our water last because it has our oxygen and our hydrogen. Hopefully I could just put 1 number here that will fix it, because if I have to change anything else, I'm going to be screwed. Okay, so here I have 2 O's and 2 H's, right? 1 calcium hydroxide contains 2 hydroxide polyatomic ions. Of course, this goes through 2 O's and 2 H's. Here, I'm going to ignore my sulfates because I already balanced them. But I do see here, I have 2 more H's. So in my product, I need to be able to account for 4 hydrogen atoms and 2 oxygen atoms. And I can do that really easily with a 2 there. And then it's balanced. You know, now that I'm done with it, it doesn't look nearly as scary as it did when I first put that up there. Do you feel the same way? Like at first blush, I was like, this is a busy reaction. I don't know. Maybe you felt the same way, but it works, right? You just have faith. It'll totally work. All right, so let's practice a few more here. So in your worksheet for chemical equations, you've got, let's see, section 1 is just a million reactions I'm asking you to balance. We don't have to balance all of them, but we should take some time to practice balancing some of them because it will help us to just practice. Really, practice is the key for these. The key. All right, so let's start here. Oh, that's terrible. I can't do that. Move it over. Okay. With aluminum and sulfuric acid makes aluminum sulfate plus hydrogen. And I'll let you guys tell me what kind of a strategy should we use to balance this. Are there any of those hints and tips that might help us, or are we just going to kind of plow full steam ahead and start putting numbers down? Sarah says, just go for it. Okay, all right, all right. All right, so if I just go for it, I read from left to right, so I balance from left to right. So I see 1 aluminum listed here, 2 aluminums listed here, so I'm gonna need a 2 there to make that work, right? All right, 2 hydrogens listed here, 2 hydrogens listed here. Well, that looks great. I can just leave it as is. 1 sulfate listed here, 3 sulfates listed here. So I'm going to need a 3 in front of here to make that work. But that changes my hydrogen, so I better go back and make sure I have a 3 in front of here to make that work. Didn't change my aluminums. They should still be good. Have a look at that. Do you guys agree with me? Yes. Okay. Now wait a minute. I told you guys it was your turn, and you're supposed to tell me what to do. And here I just did it again anyways. Okay, let's do this one right here. Calcium carbide plus water goes to form calcium hydroxide plus, looks like carbon hydride. That's actually acetylene. Help me out here. Where should I start? You tell me what to do. Ca looks good. Excellent. I'm balancing the calciums against one another. It's good. Two carbons. Two carbons. That looks good. Okay. Two hydrogens. Two hydrogens looks good. Is it balanced? Is that it? Nope. 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 All right. What I do? What I do? Aha, the OH gives me more hydrogens. Okay, so those were all good, but I couldn't just say two hydrogens gives me two hydrogens because I have another two hydrogens there. So I have four hydrogens and two oxygens. So Sarah says, yes, excellent. I need a two here to make that work. What do you guys think? Try to clean it up afterwards. It gets kind of cluttered. Now it's balanced. Excellent. Okay. Help me out with this one. Chromium plus oxygen gives me, what's that, chromium 3 oxide? Where shall I start? Okay, I'm going to need at least two chromiums. Okay, for the chromiums on the right, if I have one of those. Now what? I'm going to need three O2s. Okay, if I give myself three O2s, that's six oxygens. Then what? Then I'm going to need two Cr2O3s. Yeah. Okay, hang on. Three of these, I'm going to need two of those, which means what? I'm going to need four chromiums. Good. This is kind of fun, isn't it? A little zen, right? We can sit here, balance the equations, and feel like we are bringing order to the universe. All right, let's do this guy here. I like this a lot better than Sudoku. Just little puzzles, easy to solve. Have practical applications. Makes me feel clever. Everybody should balance equations sometime. Just need like a little book you can put on your side table to balance equations, like people have those little Sudoku books. Totally. I'd buy it. Great, Sarah got it. She says I'm going to need three CO2s because I've got three carbons here, four H2Os because I have eight hydrogens here. And then with my three CO2s, I've got six oxygens plus four waters. I have four more oxygens. 10 oxygens divided by two oxygen atoms in the molecule gives me 5 molecules of oxygen. Great. Okay. Let's do this one. Mercury 2 oxide goes to form mercury plus oxygen. Good, I've got two oxygens here, so I'm going to need a 2 in front of my HGO, which means I'm going to need 2 in front of the HG. Excellent. All right, what about this guy? Barium plus nitrogen goes to form barium nitride. Excellent. All I need to do is put a 3 in front of my barium and it's done. Well, that was nice. Okay, Haha, this one's tricky. You'll never get it. Sodium nitrate goes to form sodium nitrite plus oxygen. Now, on this one, note I can't balance these against each other because they're not the same polyatomic ion. What should I do? All right, sodium's good. If I just start and say one of these and one of these, it looks good, right? Nitrogen's good, nitrogen's good. Sarah, why two? What are you doing? My nitrogens and my sodiums look good. It's my oxygens that are a problem. Sarah says 4 NaNO3, but why? What's your strategy here? Lowest common multiple of 12. Okay, so Sarah said, look, I've got 4 oxygens on the right-hand side and 3 on the left-hand side. So lowest common multiple between 4 and 3 is 12. So if I put 4 here, that gives me 12 oxygens. And then I'm going to need a 4 here, right? So that my sodiums and my nitrogens will work. That gives me 8 oxygens. So how many more am I going to need here? I'm going to need 2 here. Is that the right answer? Maybe. It is balanced. It's technically balanced, but it's not the right answer because when we balance it, not only can we not have fractions, but we also have to have the lowest whole number ratio. And you can actually reduce this. Yes, yeah, you saw it, Sarah. Perfect. You can reduce that to 2 and 2 and 1. Okay, so that strategy that you use, Sarah, that works perfectly so long as you are always on the lookout to make sure that you're getting the lowest whole number ratio. You can reduce it further. Another option that we could have done here is to say this is 1 and this is 1. And this isn't representing 2 oxygens because we haven't said how many there gets to be here yet, right? If I have 3 here and 2 there, 3 oxygen atoms on the left and then 2, then I just need to add 1 more. So what could I make this so that that would be equal to 1 oxygen atom, even though they come in pairs? 0.5, perfect. I can make that a half. And then if I multiply everything by 2, then I'll get the same answer. There's another strategy. Does that make sense? Again, if you're like, I can't do it, try fraction. I like fractions. They're great. Okay. Haha, this one's ridiculous. You'll never get it. There's carbons everywhere. There's oxygens everywhere. What are we gonna do? We're gonna have faith, right? Hey, don't talk like that. We can do it. All right, we're just gonna start working from left to right. We're gonna have faith it's gonna work out, right? So 2 sodiums, perfect. 2 sodium atoms on each side. Yeah, you already have 2 H's on each side, so those are balanced. Nice, because you put the 2 in front of the NaHCO3, you've got 2 hydrogens here in your water. It's done. It just worked. Oh my gosh, it's amazing. It just falls into place. It's beautiful, right? I have two hydrogens. I've got two carbons here. I have one carbon in the Na2CO3 and one carbon in the CO2. And then two NaHCO3s, that's 6 oxygens, right? And I've got 3 here on the sodium carbonate. I have 1 in the water and 2 more on the carbon dioxide. It's a thing of beauty. It looked so hard and then it just worked. It was awesome. Well, that's not bad. Okay, what about this one? FeO plus O2 goes to form Fe2O3. So I'm going to need 2 FeOs because that's going to balance my irons, right? And then that gives me 2 oxygens here, 3 oxygens here. I need 1 more. So I'm going to make it a half on that O2. And that gives me 3 oxygens on each side and 2 ions on each side. And then what do? Multiply the whole thing by 2. When I do that, the 2 becomes a 4, the 1/2 becomes a 1, and the 1 becomes a 2. How do you guys feel about these? Awesome. Okay, let's take a 5-minute break, and then we will come back and we'll look at oxidation reduction reactions.